I'm doing everything I can to make that wonderful. Okay, where was your last time? I think we were talking about the Compton effect, right? Yep. Let's see how much more we have in chapter 3. We've got pair production, wave particle, that's it. We will probably finish off chapter 3 on Thursday, and then we'll be in chapter 4 by Tuesday.
What's chapter 4?
Waves and particles, matter behaving as waves. Broglie wavelengths. So far, we've been talking about the concept that photons, that light, is it a particle, is it a wave? Well, it turns out that Einstein and a few others expanded this idea to say that it's not just photons that are both particles and waves. It turns out that all matter has both wavelength and particle behavior. So you're walking around as a bunch of waves and as a particle at the same time.
Is that like get into string theory or anything? Or is that
No, it's just the idea being that the wavelengths are so small and we're so large that we are dominantly act as particles. When you get into smaller and smaller things, they become dominantly waves instead of particles. So it just depends on the scale. It started off, we're foreshadowing here a bit, but it started off this whole idea that Broglie came up with these whole wavelengths that, these describe matter. That's kind of interesting. And just like everyone else came along, everyone thought it was just a neat mathematical trick. And I could be wrong. Trying to see, but I think it was Einstein that again came back and said, no, actually this mathematical trick is something real, and there's something to this, that matter actually has wavelengths. It's funny how many times he did that. And he said, no, you guys, this is actually something real, we need to take this more seriously. Alright, so today we're going to try and get through a couple of examples of this Compton effect stuff. I was going to skip them, but I think that they might be useful. And I've already lost my chalk. That's impressive.
Is it in the corner there?
No, it's over there. Okay. So yeah, maybe we'll have our second test over
just chapter 3?
Well, chapter 3 and 4 is what I'm thinking. I think we'll it might be a little bit nicer, smaller section. And then that makes our last test large. So we can vote on that. I'll take it up to whichever way you want.
We can vote for an extra test. Let's put that last chunk in.
We can vote for 4 tests. It still only means that you can only drop 1 test, but we can do that. I'm totally fine with that.
Never mind.
Well, I mean, if every test is worth a lesser amount, that means.
Yeah, sure.
True, but then the one that you drop is also not as much.
Those are
It depends on what we got on this test.
Yeah, and we'll talk about that.
So most likely 4 tests.
Okay, so let's look at example 3.
But I'm just waiting, I think, like really quickly.
Alright, so we were talking about momentum transfers, okay? Look. Okay. And specifically we were talking about the Compton effect. So this is an example using the Compton effect. Okay, which one's which? Which one's the Compton effect? Which one's the photoelectric effect? In words. How would you describe the difference between them? Yeah, but I mean, these are the type of things, like in this class, I guess I want you guys to have, it's supposed to be an overview course, a topical course. We don't go into anything in great depth, like for general relativity. You'd be mistaken to turn around and now say that you're experts in general relativity. I've had a course in general relativity, and I would be a huge mistake to turn around and say that I'm an expert in general relativity. The idea is that we've got to feel for the very surface of everything. So one of those things is maybe to be able to say, hey, I can say something useful about Planck, or hopefully de Broglie here soon, or I can tell you the difference between the photoelectric effect and the Compton effect. That's kind of what I'd like you to take out of this course, I guess. The Compton effect, okay, they're both talking about incident photons. Okay, photons that are hitting different objects. Now, the photoelectric effect was specifically that light can produce electricity. And you can think about it right in the name, photoelectric effect. Photons come in, hit a metal surface, and they're actually creating electricity. It was really, really cool. Okay, and then we also talked about how X-rays can function in the opposite direction. The Compton effect is specifically saying that we're just talking about momentum transfer. Okay, so maybe you put that in the back of your head. These are all momentum transfer problems. It says a photon comes in, hits an electron, transfers some momentum to it, and somehow magically comes out with a different wavelength. And we also showed that the wavelength was specifically just dependent on the angle that it came back out on. It was the only thing that mattered, which was really kind of neat. Nothing else, just the angle that it deflected at, and I can tell you that exact wavelength. So if you're measuring, if you have your detector, we use detectors like this all the time, and for the plume of my thruster, what I'll do is I'll have something that's known as a Faraday probe or an RPA, target potential enamel. It's been a long time. This is nothing like 6-7 years ago. I feel old. And you sweep them in an arc. And you do these things, and you put probes, whether you're looking at the thruster or one of these Compton effects or something like that, it's because you can get data as a function of offset angle. And I just think that's kind of interesting. It's the equivalent of getting a rainbow. If I put it here, I'm only collecting 532 nanometer particles, and I move it 548, 550, it just as a function of angle, no matter what is going on. It's kind of neat. All right, so in this Compton effect, we've got this momentum transfer that is going on. And it tells us that we've got an X-ray radiation, an X-ray photon of wavelength equal to 0.05 nanometers. So this is much, much smaller than visible spectrum, which gets about 507. This is what is incident. So here we've got this photon. It's going to do bam, and it is going to smack into an electron. Okay. So, as the problem specifically reads, wavelength strikes a free, stationary electron, and the scattered photon departs at 90 degrees from the initial photon direction. Determine the momenta of the incident photon, the scattered photon, and the electron. All right, so this photon comes in, and then when it goes off, it's going to go up, straight like this. So it's going to take off at 90 degrees. Now, part A. Part A asks, what is the momentum of the incident photon? Now, something that's kind of interesting, we talk about these things as though they're separate objects. The incident photon and the emitted photon or the after photon, which isn't entirely incorrect way to think about it. A lot of times when a photon deposits its energy, it literally goes poof. It disappears. This gets back to the idea that energy is the same thing as mass, energy is the same thing as matter. So a photon can literally go poof if its energy is gone, if it's deposited. So that means that the electron then spits out a different electron, a different photon, a new bunch of energy out the other side. So you put one drop of water in this side, another drop falls out the other side. That sort of makes sense. So it's slightly different than thinking about it in terms of billiard balls. All right, so A, the initial momentum. All right, let's write down all of the equations that we might use first. I'm going to go over here. You don't have to move it because, go for it, I guess. First one, we showed that the energy is always equal to HF for the photon. Okay, and we could always write this as HC over the wavelength. Now, what was interesting is a second way that we were able to write this, and we said specifically for massless particles such as photons, we can say that it is equal to the momentum times c. This is a nice little four-banger right here in terms of energy for massless particles. So now, if that's the case, we can solve this for momenta and say that the momentum is equal to h over the wavelength of that. So we now have a very short, sweet definition of momentum for our massless photons. Next, we showed that through the process of energy conservation and momentum conservation, we get some really ugly things. We get an x component of our momentum formula that says h over wavelength is equal to something else. What this is basically saying is that these are problems that have this instant photon that's going to come with the electron. The electron we're always going to assume is stationary for the Compton effect. So the initial momentum, if we're going to look at this in terms of initial momentum has to equal final momentum for conservation of momentum, is simply due to the momentum of that initial photon, h over u. The final momentum, however, is going to be equal to two parts. H over lambda prime, the momentum of the exiting photon, plus whatever momentum that we get from the electron. Now, there's a slight problem in this. We can't just leave this without any sort of trig functions. The reason being is when this goes off, when this comes in, just as an example, this particle might go in this direction, and this one might go down in this direction. So we've got two different angles to deal with. We have the angle that the photon goes off, and we've also got the angle that the electron goes off. There's no reason to assume that they're going to be the same angle because they have different masses, fundamentally different masses. That being said, the cosine of both of these will give us back our x component of that momentum, and that's all we're interested in at the moment. So I'm going to erase this. I'm going to put in my cosine theta plus gamma u, mass of the electron u, times the cosine of phi. And that entirely describes my momentum in the x direction. Now, the y direction, the y component. We say that our initial momentum is equal to 0 because that photon is only moving in the x direction. Now here, however, we did have some sort of, the assumption is we have some sort of y component going on like this. Now, if the photon is going up, we can say that the electron is going the other direction. It doesn't matter which one you assume is positive. You can assume that the electron went up and the photon went down, as long as it's going the opposite directions. In other words, there needs to be a minus sign somewhere here. Okay. To say that these two quantities have to be equal and cancel each other. So if you put this on the other side, of course you put the minus sign on the other one. It doesn't matter. It's the same quantity. Now, these two, the y component and the x component for this momentum transfer, is specific only to the setup that we've got here. Now, you could think about it as a different problem where the electron already had some energy. What if the photon, what if the electron came at it in this direction, and then we've got the photon that's going to collide like this, and they're going to hit at some central location? All that means is that in the x component and y component over here, you have to include your components that you've got for the electron as well. It's still just a momentum transfer equation. You have to balance the equation. So not terribly difficult. All right. Now, conveniently in this problem, they've told us that this is going to go off at 90 degrees, right off the bat. Okay, so what does that tell us about the electron? Does that mean that it's going to go off at 90 degrees? Yes or no? Why or why not? Without even doing anything, what can we say about the electron?
It's going off 9 degrees.
Why?
Because we're assuming it has to go the opposite because also forces. So. It just seems like sense.
It has to go the opposite direction, right? It's going to have to go some way this way because it has to cancel this. But I can say specifically that it can't be going 90 degrees. It's the opposite. The reason being is that there's still this initial momentum that was going this way. So somehow something has to take that initial momentum with it. And it's not this photon because it went off at 90 degrees. So we know that the electron has to go off at some angle like this, that is basically going to be the y component of this and the x component of this that add up together. Does that make sense? There you go. So we're supplying harder math to the same concepts. All right, so the momentum of the incident photon. Fortunately, this is nice and easy. It's already given us our wavelength, and we can say that momentum is equal to h over wavelength. It's nice and simple. It's difficult to explain this class because most of the questions are all relatively simple. It's the concepts that are incredibly difficult to deal with. All right, so if this is the momentum, we can say that our Planck's constant is 6.63 times 10 to the minus 34 joules per second, all divided by a wavelength of 0.05 nanometers. Now, just a little note, you'll see that we put these in nanometers. As much as possible, we put wavelengths of light wavelengths of photons, I should say, in nanometers. Because we're very used to seeing 400 to 700 as our visible spectrum. If we see smaller numbers, we know that's below, we know that's in the X-ray range, or and then if we're on the other side, we know that we're in the infrared range, where we enter the longer wavelength photons. It was just a comment that I also put on your guys' tests. You guys end up like 10 to the minus 10 or 10 to the minus 8. Try and put those things in nanometers, so move it around. It makes it easier to compare numbers too. All right, so for that first one, we end up with an answer of 1.33 times 10 to the minus 23 kilograms meters per second. Then we remember the other way that we describe momentum in terms of units. Love that concept of impulse. Anybody remember the giant momentum equation that we did? What was that?
I remember it, I can't tell you specifically. There's an E in there.
Yeah, definitely.
Wait, it could be
Then it
E
changes
squared
to
equals blank thing.
No, not in this class, regular physics. Regular physics, we said that there was an impulse involved.
Let's do
J or something.
Yes, J was the impulse. J was equal to the integral of force times the time, or for your case, just force delta t. And we said this is equal to the change in momentum. Momentum is equal to mass velocity final minus mass velocity initial. Point being is that this is obviously kilograms meters per second. If we look at this has to be a newton second. And I'll go ahead and leave it to you to prove that those are in fact the exact same unit. Point of fact, you can describe momentum as either one, as newton seconds or kilogram meters per second. It's fine. All right, part A done. What about part B? Part A was easy. Part B asks in the problem, determine momentum, the scattered photon. Okay, now we need to know the momentum of the scattered photon. Great, same equation. It is the same equation. The only problem is we don't know h prime here, not h prime, lambda prime here. We need to know the wavelength of the scattered photon. So how do we figure that out? Well, this is where we get that giant equation that we use. Ooh, I was going to put it up here. The energy and momentum conservation laws, if we combine them, we get the formula that lambda prime minus lambda is equal to h over mec times 1 minus the cosine of theta. Okay, this basically says the difference between the two wavelengths comes down to a function simply of the cosine of the angle that it left at. Now, this is no surprise to us because that's exactly what we said before, that it is simply whatever wavelength it goes off of defines the wavelength. That's how we're going to get our wavelength lambda prime here. So, solving that equation for lambda prime, I can say that I've got lambda prime equals h m over c times 1 minus cosine of theta plus whatever my initial wavelength was. H is going to be equal to 6.63 times 10 to the minus 34 joule seconds. Blanked out there for a second. Mass of an electron. What's the mass of an electron? Without looking up. Does anybody know the bang of the head?
Negative 31 something.
Negative 31. You got it. There you go.
Is it 1
No.
point?
No.
Not 11.
9/11.
Oh, shoot.
9.11.
Am I just in charge?
So minus 31. Some of these, especially for chemists, are useful to know. Things like mass of electron. All right, that one times the speed of light 3 times 10 to the 8th. No one ever seemed to forget that. I won't ask because it'd be sad if you had forgotten.
Actually, 2.9.
Yeah, it's so sad that it's not exactly 3 anymore. They really did, as far as they could tell, the measurements recorded was exactly 3%.
So I'm glad this semester's going after getting basic functions.
The class is not going well, or is it just me beating up on you?
Diagnostics, probably.
Just a whole, diagnostics is sucking the life out, sucking the good grades out of every other class.
Gotcha. All right. So 1 minus the cosine of phi. 1 minus cosine of, and what's our angle here? It's theta. Oops, I keep saying 5. 90. It's that. That is the angle for theta. So cosine. Now, what is the cosine of 90 degrees?
1.
It's either 1 or 0, right?
Yeah.
So the answer is, in this case,
Calculator.
And if it's zero, then that's a really boring equation.
It had to be zero, right?
It has to be zero. Here, I want to mentally show you guys this, because these are useful to always remember. Let's say we've got a triangle right here, standard triangle, here's our theta. If I want to take the cosine of this, okay, by definition, the cosine of theta equals, adjacent over hypotenuse. Okay. Now, what happens as this starts to go up? Let's start saying that this angle starts to get really big. This is already a 90-degree. So I've got like this, and then I've got this. As this angle, as theta starts to approach 90 degrees, the adjacent side drops to 0. Okay? And that's the way to think about it. Just mentally, you can think about getting bigger and bigger and bigger and bigger. If that's the case, then the cosine of theta approaches 0. Now, the opposite is true for sine, of course, because sine is the opposite side of the hypotenuse. This is really, really close to the hypotenuse in length. This is almost an isosceles triangle. Therefore, the sine approaches 1. It's good to be able to have a way to do that without having to take out your calculator, is my point. All right, so cosine of 90 degrees. This just goes away to be 0, which means this whole quantity is just equal to 1. All we need to do is solve for that. Can you get me on board?
Gotta know what you have to subtract. You have to add your.
Yes, sorry, I didn't put that in there. Plus 5. So, if we run the calculation on this, which I did, I get an answer of 1 equals 0.0024 nanometers plus 0.05 nanometers. Now, there's a lot of times, and this is my fault, I'll take the blame for this, that when we're dealing with special relativity, general relativity, when you have tiny number plus bigger number. Now in this case it's not that big of a difference, but your calculator can't handle both simultaneously. So what's easier to do is leave off the bigger number, just calculate the tiny number, and then write it out like this. Some of you guys did figure this out, I noticed on the review when you were going through the general relativity and special relativity. That's how you get your calculator to do this, to handle this. I guess I should have been more explicit about that. Alright, so lambda prime is equal to 0.0524 nanometers. And we can say that's approximately a 5% difference from our lambda, which of course is equal to 0.05 nanometers. So this wavelength has gotten approximately 5% longer. Now, a longer wavelength actually means less energy. So if we go over here and look at our energy function, energy is equal to hc, which is a constant divided by the wavelength. It's the shorter wavelengths for these protons that have the high energy. The longer the wavelength, it's the lower the energy. So X-rays have a ton of energy. That's the reason that they knock these electrons all over the place. That's why you can get X-rays, and they're really cool things. In the visible spectrum, there's actually very little energy. And then you get to the infrared, and there's even less. All right, next. What was the next thing they wanted to know? Part C, what was the momenta of the incident photon? Okay, so we're going to erase.
Did we find?
We didn't even find the. We just.
I'm sorry, you're right. Okay, let me finish that off. Now that we've got the new wavelength, now I can say the momentum prime. I should really label that as prime over there. P prime is equal to h over lambda prime. So 6.63 times 10 to the minus 34 joule seconds divided by our new wavelength, 0.524 nanometers. And we're going to get a momentum of something that's on the previous page.
1.26.
There you go, 1.26.
That's the next
Kilogram meters per second. Okay. Now, likewise, if the energy is lower of our exiting photon, we would expect the momentum to be lower. And in fact, it is. Okay, so it hits some object. It is imparted some momentum to the electron, and it goes off with less. Okay, now you can go ahead and bring me back. I'm going to go to right at the top of A. Right where A is. Part C. momenta of the electron. All right, so this gets slightly more difficult. Now, question B is we had some sort of incident momentum, and we had some sort of final momentum for the particle that exits. So, can't we just say that incident momentum minus the momentum of the particle is equal to the momentum of the electron?
Well, since you said this was hard, no.
Okay, but why not? Why can't we do that? Why can't I just get away with saying, all right, 1.33 minus 1.26, done?
Because of the angles?
Because of the angles.
And momenta.
Yeah, or momentum. You can say the momenta or the momentum. They're both correct.
Okay.
Well, that was the limit of sparks for today.
That was what?
That was the limit of my sparks for today.
Okay. Yes, no, the angle is correct though. This is in two different component form. So we have to handle the components separately. This would be nice, but we can't do that. All right, there's an easy way to do this, and there's a hard way to do this.
Easy way.
No, hard way first. We'll do both. We got to do the hard way first. In the event that you can't do the easy way, but you can't go.
So you have the power over that.
Yeah.
So,
And you know we're not going to consider the hard way.
I
now,
don't care
it's
about
easy way.
momentum of electrons when I'm checking people's eyes.
Yeah, you will.
Too bad.
Isn't that exactly what you're going to care about?
Okay,
No.
so we're going to figure out the momentum. To do this, we're going to do it based on components. So here is I will make it slightly easier. We could solve this for the full component here, for the x component, and then solve the full y component, and then try to recombine them. Or if I can find a way to get rid of these, then I can do it all at the same time. I'm going to use both those equations right there. So I've got h over prime, or lambda, I mean, h over lambda prime times the cosine of theta, gamma u n e, times the cosine of phi. I knew there was something missing. Cosine of phi, and over here is 0, equals h over lambda prime sine of theta, minus, don't forget the minus down here, because in this case they're going in different directions. Okay, right off the bat, we already know that the incident photon is going off at 90 degrees. So we said to begin with that this whole quantity, this is 0, which means this whole quantity just goes away. Likewise, this sign of 0 is going to be equal to 1. So we end up with just this quantity over here. We can now put this on the other side, and we have that positive quantity. I can rewrite these two equations now more simply as h over lambda is equal to gamma u me u cosine of phi over h over lambda prime gamma u me u sine of phi. All right, here's a neat little trick. We have two equations. Now the thing that we're interested in is this quantity right here. We want to know what that is equal to. All right, fine. Let's just divide both of these equations. We need to know this, but we also need to know our angle. Let's attack our angle first, because that's going to be a little bit quicker.
So does that mean the left side's going to go poof, basically?
Well, lots of this is going to go poof. I'm going to divide this whole one right here by this one right here. The entire thing. Okay? So if I do that, I can simply say that the h's are going to disappear, and I'm going to end up with my h prime over h. So I've got that over underneath.
Your h prime over h.
Where's the h prime at?
Sorry. Lambda prime over h. So if I divide 2 by 1, on this side, I'm going to end up with, here, I'll show it out loud. H over lambda prime divided by h over lambda. What is this equal to?
1 lambda over lambda prime.
Yeah, so it's a little confusing when you write it like this, but this is just equal to lambda over lambda prime. Now, when I divide this whole thing by this whole quantity divides out, and I end up with just sine over cosine, which is equal to the tangent of phi. Neat little trick. So I can take the inverse tangent of this, tangent of lambda over lambda prime, and I'm going to get my angle phi back. Ta-da. If I throw this into my calculator, my lambda is 0.05. Lambda prime is 0.0524. If you're putting this in your calculator, take a shortcut. Forget all the decimals, and you can just do 500 divided by 524. Anyways, what do you get for an answer? What'd you get?
43.7.
43.7. Nice and simple. Yay! Now I can use
Set
this.
500, but I didn't do that.
You can do it either way. I'm just saying that you don't have to put in all the freaking decimals. It's easier to do like this. Okay, now I can then take this angle and plug it back into either one of these equations. Either one of you have a preference? Kyle or Rick?
I want some.
You want sine. All right, let's plug it into that one. Then I can solve for this, and I can say that I've got h over lambda prime times the sine of phi is equal to my momentum of the electron, which is this quantity right here, the total momentum. So let's go ahead and put numbers into that. It's at 6.33 times 10 to the minus 34 joules seconds, all divided by, we've got 0.0524 nanometers times the sine of 43.7 degrees. What do we get for an answer? Stop looking at your book.
I had to buy it, so I'm going to use it.
6.3.
You have a point.
Yeah.
If you want to have the book, you should fill it up.
Wait. No.
Okay.
Better. 6.63. Sure. Actually, I think I got something slightly different in the book.
Well, see, like, all of the answers I've been getting have been slightly off from the book, too.
So the book around the summary you did.
Yeah.
This one looks
book
good.
is wrong.
Did you get the 1.83?
Yeah.
Okay, good. So, the momentum of the electron is 1.83 times 10 to the minus 14 kilogram meters. Okay, that was the very hard way to do it. Now, let's talk about the easier way. I'm going to leave that over here.
I thought that was easy.
Yeah.
No, that was the hard way, actually.
Well, I say that, but I'm still going to forget all of this. So.
I
Yeah.
hope not. And we're about to talk about that when we come back.
Diagnosis takes all the information my brain can hold. I spent 8 hours in lab yesterday.
I do have 8 hours to spend in lab.
All right, so I need my initial momentum. It said it's what? 1.33 times 10 to the minus, what are we getting here? 10 to the minus 23rd kilogram meters per second. My exiting photons was 1.26 times 10 to the minus 23rd kilogram meters per second. Now, here I will take the fast way to solve this. We said that we couldn't just do P minus P prime to get the momentum of the electron, which was true. But geometry can help us a little bit.
Can you just throw cosine sine?
Well, it's kind of. I'm saying that I've got an initial momentum that is coming in here that is P. Okay? Now, I've got some sort of also momentum that goes off here as P prime. Now, what is the momentum of the electron going to be? And no, it's not going to be this, because that doesn't make any sense. Because that means that all of a sudden the momentum of the electron is going to be greater than the momentum that we had of the other two. That doesn't work. Okay, the way that we can do this, however, is to say that we know that P prime, if I move this down like this, I can say that P prime over here plus whatever the momentum of the electron is has to get us back to P. So although it's the same magnitude, this is important. This has to be our momentum of our electron to get us back. But even this doesn't work because I'm adding here, and then I add this, and that goes over there. So I'm going to put the arrowhead on the other side. Like that. That'll be my momentum of my electron.
Because it's going down.
Because it has to go down. That's a really weird way to look at it, though. But you can say the momentum prime plus PE gets us back to P. Here's the easier way to look at it, and the way that your book has it, is to say that P prime momentum of the electron.
That's what I thought you were going to
So it's just a little weird because this is shown down here below the axis instead of above it, even though we know that this is going north. But these two add together. So if we do that, what can I say that PE has to be equal to in terms of a number?
Those two.
Okay.
Yeah, flagging there.
There you go. I can say that this is going to be P squared plus P prime squared. You don't have to bother plugging in. You can just assume that it works. Now, simultaneously, the very fast version of it, to say phi is going to be equal to what? In terms of P and P prime.
Oh, this is backing up all the
No. I mean, not quite. So we've got P here, P prime, PE, and now we want to determine phi. I found a very easy way to figure out PE. Just the Pythagorean theorem. What about phi? Phi being this angle right here, because this is the angle that the electron's coming down. Yes. Which one do I want to use? I want to use P and P prime. There we go, yeah. It's opposite. And anytime you're not dealing with the hypotenuse, you know you're with the tangent. So I can say that this is going to be the inverse tangent of my momentums, and I can say it's the opposite over the adjacent, P prime over P. So this very lengthy process that we went through to get this, we said that we had lambda over lambda prime. So why does this give us the same answer that this does? And if we look at this, let's figure out what this is. This is the inverse tangent. If I put in there,
How's it just using Planck's constant?
right, because the only difference is Planck's constant. So this gives me P prime, or I'm sorry, this is going to give me H over lambda prime over H over lambda, which is the same thing as what we had lambda over lambda. So they invert because they're underneath. It's the exact same equation as this over here. This took us a lot longer to get to. We can simply do this right off the bat.
So,
Ta-da.
what basically differentiates when we can use easy way versus hard way?
So, we get back to the very first question that I asked when we started this. I said, can I just use this? And the answer is yes. You can always use this. If I add something to it, what do I have to add to it?
Components?
Kind of. Yes, but what's a way to do that without actually writing components?
Square both of them.
That works too. I'm kind of leaving you. What happens when you put components back together? What do you get? The whole, which is known as a. What is the whole of anything that had components?
The sum?
Not a scalar, but a
Vector.
There we go. This is true.
Whee!
Nobody likes vectors. It takes a very long time to like
Watching the
vectors.
calculator.
It was interesting in regular
Yeah.
physics, but so it was interesting in regular physics.
Like good vectors are linear, and people just don't like them a lot.
And you just get used to them after a while, I guess, as a physicist. And then when you finally become okay with vectors, then you have to start dealing with tensors. And then you hate tensors. And I've never gotten past the fact of hating tensors. I still hate tensors. Okay, this is always going to be true. Even, we just have to make sure that we're using relativistic versions of the momentum for all of these quantities. So even though we have to use relativistic momentum, that doesn't mean that you still, the vector addition for momentum transfer isn't true.
So in other words, the equation with the vectors is the same as P equals the square root of 2.
Yeah, because it works out the
Now,
exact
if that
same way.
angle at 9 degrees, they just start everything off, right?
Yeah, that'd be a real pain in the butt. Which isn't to say that you can't do it. Then you'd have to start using things like law of cosines.
No,
No.
Okay, do it the long way.
I don't remember this, I don't care.
Giving you options. You just don't want options.
We love the option of doing it the easy way.
We just want the one way to do it, and I think so.
All right, do it this way, and then you'll always get the right answer. It's slightly longer. Now keep in mind that's only for the special case where you're coming head on. But the problem that I have for your next test is you're coming at an angle like this, and this is moving at this angle, and it's in 3 dimensions. So you got to include the third dimension.
So we're going to go to get rid of that question.
I'm kidding, of course. I'm not going to have that.
Well, I've been through this semester. I will. Not
All
just
right. kind of waiting to several pages of my notes.
Something like that. We never, I never really say what we're supposed to.
Okay, so then the question becomes, when we were doing this, do I have anything on my bottom of the screen? Oh, yeah, here we go. Question becomes, we spent the last 2 weeks, not counting our tests, wondering or figuring out particle theory for all this stuff, figuring out how photons act like particles and describing their behavior. Now the question becomes, why on earth did we ever describe them as wavelengths in the first place? Why does wave theory matter? Is it even still relevant? Turns out that photons still, the photon theory that we're going with, we could just start with physics 1 and teach photon theory to begin with, right off the bat for all momentum transfer. The same way we could, whenever we're talking about how velocity equations work, we could just do all our kinematic equations using special relativity. We could teach that right off the bat. Because remember, special relativity is still true in Newtonian dynamics. It just breaks down and a bunch of the terms cancel. So the point being is that photon theory always works, just like special relativity always works. It's just cumbersome and obnoxious. So if there's a shortcut, which it turns out that there is for longer wavelengths, just use wave theory because it's easier. Or if you're doing slow things like on Earth, because you're just tossing a baseball, you don't need relativistic calculations with a baseball. Just use Newtonian mechanics, which are complete enough to give you the right answer. So, for example, if we reran this using a wavelength equal to 500 nanometers, which is what color?
Orange.
That's 600. I know that was the answer like 3 times in a row, but no.
That's the only one I got right.
Gotcha. No, it's more like an aquamarine. This is right on the border of. In fact, it'd actually be pretty close to the Mountain Dew. Most people say that Mountain Dew is a pure green, but you can tell when you compare it against a different green, there's actually a considerable amount of blue in the Mountain Dew. Yeah, you don't notice it when you look at it until you compare it against a different green.
I guess you look at compared to like the wrapper that's more green.
Right. All right. So 500 nanometers, kind of an aquamarine, kind of a Mountain Dew green. If we were to calculate this whole thing, the Compton effect of a photon coming in, smacking off an electron, we would see the photon come back out with 500 nanometers. It would come out with the exact same wavelength, or close. What it actually turns out is that this is going to be 500.00001 nanometers, and I made that number up. The percent difference is going to be on the order of 0.0, I forget. 0.005% difference.
So you take a lot of photons, it's a big number, right?
No, because every single time this happens, all photons are going to come back off at the same exact wavelength. So in other words, when you try this for visible light, if I send red light in and I bounce it off electrons, I'm just going to get the same wavelength red light everywhere out, which makes it treated like it's wave theory. The idea being that a wave comes in, hits an object, and that object pushes the wave back out. Just like we're talking about the barrier. If a wave hits a barrier, it pushes it, and it makes the same wave on the other side. A barrier can't magically, think about this, if you had a floating buoy, and you had one wavelength on the one side hitting, and all of a sudden it was changing the wavelength on the other side. That doesn't even make any sense from the point of view of looking at it, because the buoy is either bouncing up and down at this wavelength or this one. It can't possibly bounce up and down at 2 different wavelengths. Blah. So, if this is true, if the wavelength is coming out at the exact same, or nearly the exact same that it went in, what can we say about the energy transfer to the electron? I'm in quantity. Is it large or small? Yes. Look at your equations if you need to. I'm just going to have multiple choice test of these type of questions on the next exam. That's what it's going to be. Drew, what do you think? Small energy or large energy?
Small.
David, not Drew. What?
I don't know. Large.
We got to vote for small and large. What else can I hope for in life?
I mean, it's on the bottom.
The answer is going to be very, very small. If the wavelength comes in with the same wavelength that it went out with, not much happened is the whole point. Not much has changed. Which is to say that the electron can't transfer much energy. We can also go over here and look at this. What happens when the wavelength is large? the energy of the photon drops to nothing. Same thing is true for the momentum. So all of these effects that we're looking at are only really useful in X-rays in very small wavelengths, smaller the wavelength, which kind of makes sense because if you got a wavelength that's like this, that's lower energy than a wavelength that up and down like that. That is crazy. It's a whole bunch of energy. So the point being is that the electron doesn't even really move. The energy comes in and the electron acts like basically a wall and this bounces off. So that photon didn't have enough energy to actually transfer enough to the electron in the first place. Okay, now this leads us to the idea of the correspondence principle. And actually we were just talking about that a second ago. Correspondence principle. Okay, correspondence principle, which again sounds like a Big Bang Theory title, simply states that any of these theories that we come up with have to jive with the old classical theories. In other words, remember when we broke down special relativity and we showed that if you're dealing with large wavelengths, we just get our Newtonian mechanics back. Everything just falls out, and we end up, like for kinetic energy, for example. Remember when we said that Ke is equal to gamma u minus 1 times mc squared. And I was really bummed that some of you guys couldn't come up with this on the test. No difference between the three. But in any case, we broke that down because in here, there's the velocity squared and the c squared. Now we showed that if the velocity for this is really small, then we can just get our 1/2 mv squared back. When v is small, using the binomial expansion theory, we showed that this is true. So the whole point being is that the correspondence principle says, great, we found something that describes these photons and this Compton effect. What happens when they start to get to larger wavelengths? Does it go seamlessly into wave theory? And the answer is it does. But it's an important thing to note, an important thing to rate, because otherwise we might have a theory that works for the fast things and a theory that works for the small things. We start to get to the middle, neither one of them works. That ostensibly could happen. And then we have a real problem that means that either of them or both of them are wrong. So, all right, next.
Exam time?
Go. Not texting right now.
Huh?
Not texting right
It's for the stupid group diagnostics.
Thank
It's kind of a, I gotta tell them things.
You can let them know that I will come down on you, and then so.
Can I
So is that all the
can I tell them I get out of here
correspondence
around 5?
What? That's it. And the book just mentions it, and I think it was an important thing to mention because we're not going to go through the example like we did with this to show that it delves into wave theory. At least not yet. We will in the future.
Okay.
But yeah, the book mentioned it, and I thought I would follow along for those of you that are reading the book. Okay, so next topic. All right, let's get rid of this. Or actually, there's another simple example that I at least want to get started with, and then I want to talk about your tests. Yeah. I was hoping Brad would be here right now. Okay, so that first example that we were talking about wasn't an example of, and really you can't not wait.
Sorry. Kind of know. Sorry.
Well, if you need to, then go. But
No, I can. No, I just got some text. No problem.
oh God, please.
I'm sorry. I will wait.
Appreciate it. 15 more minutes. All right, the first example where we had the photon bouncing off the electron. Is that an example of inelastic or elastic collisions?
Use it bouncing so much.
Elastic, because it's bouncing off of. Okay, so all this same stuff still works with inelastic collisions. Now, there's two types of inelastic collisions. Do you guys remember what they are? Yeah, you got it. What are they?
When they like collide and move together as one object,
Or
or they both just stop.
no, but it's the same idea. What's the exact opposite of that? Do the hand gesture in the opposite direction.
They is that explode?
There you go.
Okay.
Explosions. So an inelastic collision is actually in either direction. It's where stuff sticks together, like we talk about the train cars coupling and then they move off, or the example where we blew up coconuts and things like that, if you were in my 2211, which most of you guys were not. Anybody in my 2211? Brad is the only one in my 2211. Oh, okay. So we talked about exploding things all the time here. Also an inelastic collision. So the example that is up next is the photon that comes in and hits a helium atom. If this hits the nucleus of a helium atom, which has 2 protons and 2 neutrons, it's going to break off into 1 proton and 1 neutron each. So here's helium. It's an
Photon.
explosion. What?
There's a photon.
It's a photon coming in. It's hitting the helium nucleus, and then we have 2 things that go off on the top and the bottom.
So then we get hydrogen.
What?
So then we get hydrogen.
Ah, that's my question. What are these things called?
What did you say? What's called?
This is a proton and a neutron. And this is a proton and a neutron. What do we call this?
I want to call them isotopes. So I'm sure that's
It is an isotope of that, so that's fine. It's an isotope of hydrogen,
Ion.
also known as heavy water. Does that give you a clue?
What is that term?
Deuterium.
Oh,
See, you've got a couple of them.
Isn't that?
What?
I knew that.
Well, you didn't say that.
Well, because I was busy drawing.
Okay. So it's deuterium. So as we break this up, we have heavy water, we get deuterium. So the idea being is we need to figure out the momentum transfer between this. So, A, if we have this coming in, we can say the atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. And just a little aside here, this annoys the crap out of me. The atomic mass unit is 1.66 what?
Oh, that's example 3.4.
Yeah, I didn't bother to change that. Okay, we're going to blow through this example kind of quick. U is equal to 1.66 times 10 to the minus 27 kilograms, which is obnoxious because this is neither the mass of a proton, neither the mass of a neutron. This is smaller than both. What's the mass of either a proton or a neutron? They're nearly identical, but not quite.
1.67.
1.67. Now, which one's more massive?
The neutron.
Neutron. Neutron's about 1.674, something or other.
Yeah.
And I think a proton's 1.672. Okay, so neutron is ever so slightly larger. And sometime maybe I learned why the mass of atomic unit is 1.66, and it's not even exactly this. If you look it up, it's 1.6600 something, 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 something terribly obnoxious. I don't understand why they didn't just make it equal to 1 proton, or something to that effect. Now, my guess is this is that they thought that this was the mass of a proton at the time when they first made it, and then they later realized that the proton's a little bit heavier, maybe. I don't know. Okay, but in any case, we can say now that the helium nucleus, the mass of the helium nucleus, which I'm going to record as MH, is equal to 4.00151 U. That is the mass of this. Now, we have the mass of deuterium is 2.01355 U. Now, we're going to say that each one of these goes off at 0.6 C as well. So they are moving. So we've been sitting still helium, and all of a sudden it blows apart into these 2 different particles and moves off at the speed of light.
And that's
Now-
bigger than bubbles.
And it's what? No, what were you going to say?
Is the point of this because if you times that 2 by 2, it's bigger than that 4?
Exactly. So the energy of the photon both goes into the kinetic energy of this particle here, of each of these particles, but also goes to increasing the mass of the products. Both things can happen simultaneously. So when we look at this, we have to do an energy conservation. We can say that the energy of the photon has to be equal to the energy of the photon on the way out. Or actually, let's do it this way. Energy of the photon, this is the before, plus the energy of the hydrogen, or helium, my bad, is going to be equal to 2 times the energy of the deuterium. This part is not in your book, so. Now, that is just a before and after energy equation. We've got EP plus EH equals 2EP. That is just energy conservation. Now, the trick is to figure out what the energy of each one of these individual ones is. The book makes, I don't want to say a bad habit, but often jumps pretty deep into the math. It's easier to just start off with an overarching equation to figure out what we're even looking at. What do you got?
What's the pH and DV?
P, energy of the photon, energy of the helium, and energy of the deuterium.
Okay.
2 of them. Now, energy is a scalar, not a vector, so we don't even have to worry about silly vector signs, which is nice. First one, what is my energy of the photon going to be? What is the energy of any photon?
Momentum times light.
Okay, there we go. So we've got it over there. I can do momentum over the speed of light, but then we have to figure out what this is. I'm just going to shortcut it and go to this, hc over lambda. This is easy. So this is hc over lambda. So the energy of the photon is just a function of its wavelength. Doesn't that seem interesting? What about its kinetic energy? What about, doesn't it matter how fast it's going?
So it's going to see speed.
Yep. Okay. But in the back of your head, you always have to have that as that quick answer. No, it doesn't matter because the photon is always going the speed of light. So the only thing that ever changes the energy of a photon is its wavelength. It can't have different energy levels. It has one energy level, always. Now, what about the energy of helium? What's this energy going to be based on? What's the helium doing?
It's rest energy.
It's doing nothing. So it has, as far as we know, rest and rest energy or mass energy. They're the same thing, which is simply equals mc squared. That is all that it's doing is hanging out there. Now over here it gets slightly complicated. Mass of electron. I'm sorry, no, mass h. My bad, mass h. C squared. Over here we have 2 times the energy of the deuterium. Now the deuterium is moving. Now, handily, we have the equation. We can either just talk about the rest energy, the kinetic energy, or the total energy, which I know some of you made the mistake of putting on your test. So this is just going to be 2 times gamma u times mass of deuterium c squared. And now we've got our equation that we can work with. And this is my point about starting at an overarching idea. If you just write this equation down, like I don't know what we're doing. If you can start off with simpler concepts and get an idea, okay, this is just energy conservation, and then plug in the terms, it's a lot easier to do. You might try this for your homework this Thursday as well. Yes?
So, are we assuming that both of those values are moving at the same velocity?
Yes, 0.6 c. We can going forward with this. That's why the energy is going to be the same. Okay. And then we can show that the angle has to be the same because they're the same mass and whatnot. Okay, I'm going to stop here, and you guys can actually probably finish this example off. I wanted to show the energy conservation. Now at this point, it's just solving that. You can text if you want. I'm going to hand back your test right now and the solution guide, and I want to talk about it, so no going anywhere just yet.
Am I right?
What?
Oh, I guess I did text you too.
I'm very sorry. I know you disagree with texting.
Alright, oh, and this. Okay, things that went wrong. We'll go through. On the first problem, the first part, people for the most part did well. There was a couple errors wondering as to whether or not we use the time dilation formula, the shortened version, or we use the full formula. When in doubt, always use the full formula. Okay, you can't go wrong. If you use the full formula that has the gamma v, and you can see on my exam proof of how to do it, you're always to get the right answer. In the event that x equals 0, then you get the shorter form anyways. So it's a little bit easier in that case. But for this problem, you couldn't use the shorter formula. You wouldn't get the right answer. And the reason being is Bob's position is not 0. Bob is up here at the front spot. He's up here. His x is not equal to 0. He's sitting at a position up front. And you might ask, what difference does that make if he's thinking about a time 0? His position's always the same relative to where this was going. It matters because that was not the position where the clocks were synchronized. Anytime we use the simplified time dilation assumption, we're using it where these clocks were synchronized. All right, I guess you can probably look through the rest of number 1. Number 2 was just putting your kinetic energy equal to your rest energy. The only problem that people really ran into here is if they use the wrong energy function, or if they use a non-relativistic kinetic energy. You can't just say it's equal to 1/2 mv squared. You have to use relativistic kinetic energy. C, I had lots of different problems. One of the problems is sometimes people use too small amount of time during the test. Retroactively, I guess I would have told you guys to use a larger amount of time. If you use a day or a year, then it becomes much easier because you can get the results. You could give me your answer in terms of fractions or percentage. I accepted any of those. Okay, first on the grades. I wrote red all over your papers. You'll see where I marked them wrong. And I started with a rubric, okay? I kind of let the rubric go, and then I kind of sorted them in order of how I think you did, and then I put a grade that was largely pulled out of error. Okay? If you guys want and you feel like that grade is not fair, you can give them back to me, and I'd happily put it against the rubric. I don't think that will fare well for you. And I'm not saying to tell you not to do that. I'm just saying that I was trying to give you the benefit of the doubt because in some cases they were pretty rough for some of the problems. But I would be happy to regrade them accurately against the rubric I had. The second thing, all three of these problems were based on direct examples we did in class that are in your book that we did in class. And that's why I guess I'm a little bummed that it didn't go better. We did these in class. We did the spaceship problem exactly in class. The second one, the kinetic energy, shouldn't have been too bad. And the third one is the same problem, just with the one number divided by 2. Half geosynchronous instead of full geosynchronous. I don't know how I can help more. I know that I talked most of you guys into taking this course, and I'm glad that you're here. And I know that I'm at least friends with or acquaintances with all of you guys outside of class. But we need to at least take class a little bit more seriously, I guess. If there's any way that I can help you guys with the material, if you want me to help you study outside, I'm fine with that. But I want to see us do better on this test. Okay, that's all I got. I'll see you guys later.
Which one is the big one? I don't understand.
Yeah, okay.
I thought one was negative.
No. It doesn't matter because it's the difference. So you've got 1 minus this change. The difference in this is going to be a difference in this. So the time dilation, according to this, is a bigger effect than the time dilation according to this. Okay, well, I think I just want to mention that you guys will probably go to the and
I took anatomy and
I need you guys to
and
work.
nothing else.
And I'm not saying you didn't or anything like that.
Yeah,
I'm
if
just
you
saying
short English version,
you
then
have to be careful. That goes for everybody, but I mean, because obviously, if you do something, I want you to assume
mix it
I did it by myself.
Yeah.
I'm not saying that you didn't, I'm just saying you had the exact same thing.
I compare what now I lost ground.
Oh, yeah, I got that same thing too. Good. We probably did.
Right, and you guys did really well on that one. I just feel going forward, I don't want to be in that position, but things don't need more being done.
Our group of 7 people will have over 140 samples that we have to do in the next 5 years.
How many you have through?
This is the beginning of the second one.
No, how many samples you got through?
I haven't gotten in.
How many do you need to set right now?
I am on a total of 6 different patients right now. And everything's just really screwed with time. So, it is, people have, there have been 2 women in there that have literally broke down and cried over this. So.
Is this like how you can make people switch their majors?
Yeah, pretty much. Except most people would have switched their majors before they got the diagnostics. By the time you get the diagnostics, you don't have a choice to switch your major.
See, ours, we have a slight choice because, hey, you can switch from a chemistry grade to a chemistry concentration, and that means you don't even think all of a sudden.
Well, I mean, we can go from biomed to regular biology, but not
Yeah.
very many people get into
That's what
med school with regular biology degree. So,
yeah.
so I just need more than 24 hours in a day, and that'd be great.
Nah, I could use more.